let's get started. So before proceeding with today's lecture, I just wanted to kind of orient since we're at the end of the quarter now. So this is the final lecture that either I or Tatsu will be giving. So now let's begin today's lecture. So last time, Tatsu gave an overview of RL from verifiable rewards, and he talked about policy gradient algorithms such as PPO and GRPO. This lecture, we're going to deep dive into the mechanics of policy gradient GRPO. So we won't necessarily cover new material, but just to take the existing material and go a bit deeper, show you code, and some math as well. Okay. So just to kind of remind us what we're doing. So we're doing reinforcement for language models. And in reinforcement learning, you have to define the states and actions and rewards and so on. And just to be very clear, I think this hopefully should be obvious by now, but just to state the obvious. So the state is the prompt plus the response that you've generated so far. And each action is generating a particular token, the next token, okay? The reward is essentially how good the response is. And for the purpose of this class, we're going to focus on outcome rewards, where the reward is a function of the entire response. We're going to focus on rewards that are verifiable. So the computation is deterministic. Some function just returns a reward as opposed to having to ask a human. And in this setting, typically in reinforcement learning, you see notions of discounting and bootstrapping, where it's multiple turns where you're getting, and that really makes sense when you have rewards in the middle. If this is more of kind of a, you just generate a bunch of actions and you see if your answer is correct. So that obviously introduces a bunch of difficulties because it's very sparse and delayed reward, but it also simplifies, I think, some of the conceptual thinking around this. So for example, you might have a question, math problem, and then there's a chain of thought, you rethink for a while, and then finally the language model might generate, therefore the answer is 3 miles, and then the reward would have to extract the 3 miles and see if that matches some ground truth. So in reinforcement learning, typically people talk about the transition dynamics. It's very important. In this case, in the language model setting, it's very simple. It's just the plus operation. You just append the action into the state. This has a number of important implications because you understand the dynamics of the world, you can do planning, aka test time compute. And this is something that roboticists would only dream of. If they had a transition dynamics of the world, they could simulate and they could do all these things. In language modeling, we can do that, but not true in general reinforcement learning. And the other thing to kind of realize is that the notion of state is really made up, right? If you think about reinforcement learning in the context of robotics, the state is the joint angles, the position, maybe an image or something. It's really much grounded in the real world. Whereas language models, the state is just tokens that the language model happens to generate. And this introduces a lot of flexibility. It introduces a lot of degrees of freedom where the language model can kind of make up its own scratchpad in order to arrive at the final answer, whereas often a robot is very much limited by the external world in terms of what states are even achievable. So the issue here isn't about reaching any state, which is often a challenge in robotics and control. You can't even reach the state. Here you can reach any state you want by just writing down tokens. But the challenge is making sure that these tokens actually lead to some ground truth answer that's correct. So I think it's worth reflecting on. It's all reinforcement learning, but the intuitions and what's hard and what's easy kind of changes in the language modeling setting. Okay, so the policy in this case is just a language model, action condition on the state, which is the prompt and response given so far. This is often fine-tuned from an existing pre-trained language model. And then there's multiple names for this, rollout, episode, trajectory. In this outcome reward setting, you start with a state, you generate a bunch of actions, aka tokens, you get a single number, which is a reward. And then your objective is to maximize the expected reward, where the expectation is taken over prompts, which the environment gives you, and also the response tokens, which your policy pi that you're optimizing gives you. Okay, so hopefully that's makes everything kind of very grounded and precise. Okay, let me know if you have any questions about the setup. So let's now talk about policy gradient, which is a whole class of methods for learning the policy, which essentially start with the policy and try to improve it using gradient methods. So for notational simplicity, we're just going to let A denote the entire response instead of a single action. Because we're in the outcome reward setting, it doesn't really matter. You can just think about the actions as being all generated at once by the language models, and then you get a single reward at the end. Okay, so remember we want to maximize the expected reward with respect to the policy pi. So just expected reward is integral over the distribution over states times policy of action sequence given state times the reward. So this is pretty straightforward. And policy gradient says, do the obvious thing. You want to optimize something, let's take the gradient. So you start taking the gradient. So the gradient only touches the policy. And this is the key trick. It's like the policy gradient theorem, some people call it, but it's really just the chain rule for log. So this basically gets rewritten as a pi and then the gradient of the log. And then I'm going to rewrite it in terms of expectation. So expectation is hiding basically the distribution over S and A here. Okay, so this form should be very familiar. So this is the gradient of the expected reward. Okay, so naive policy gradient basically says, I'm just going to sample a prompt from P, sample a response from A, and then I'm just going to update the parameters based on whatever's inside this expectation. Okay, so think about if you're doing SGD, you look at the expected loss, and you just sample a term, and you just evaluate and go with that. So interpretation, this is essentially the same as SFT, except for everything is weighted by the reward. Okay? So in SFT, a human being writes down A for you, and you just mimic A and update the parameters and maximize the probability of that action. And now A is generated by the model, but you get to hit it with a reward. Okay, so just as a kind of an intuition building, so suppose that the reward is either 0 or 1. Is it correct or wrong? So in this case, the naive policy gradient is just going to only update on the correct responses. So R is going to be 0 for the actions that lead to incorrect responses. So those are going to be completely ignored. And then on the correct responses, R is 1. So you just essentially sample, you select the responses that are correct, and you just do SFT on this. The only difference is that the data set is changing over time, because after you do an update, now you have a new policy, and you generate the data set based on that policy, and you iterate and so on. But this is very natural. And the only challenge here is, not the only challenge, the main challenge is that people talk about policy gradient as being high noise or high variance. So in stochastic gradient descent, if you're doing supervised learning, this is also can be the case, that your gradient is very noisy, and typically if you use larger batch sizes and just kind of keep on going, then it sort of empirically seems to work out. Reinforcement learning is a kind of whole nother level in terms of noise and variance that you have to deal with. So in particular, if you look at this setting where you have 0 or 1 as a reward, think about solving a hard math problem, right? So in this setting, the sparse rewards, the rewards are sparse, which means that very few responses are going to get reward 1. Most are going to get 0. So if you have a bad policy and you roll out and you generate actions, most of your rewards are going to be 0, which means if you look at the gradient, you're basically making a 0 gradient update. So if you're in a setting where your policy is so bad that you're not able to get rewarded at all, then guess what? You're not making any gradient updates and you're sort of stuck. So that's a pretty bad setting to be in. At least in supervised learning, you're at least making an update towards something. You're guaranteed to make an update towards something, but in reinforcement learning and sparse rewards, that's not true anymore. Question?
Why is the data set changing?
So the question is, why is the data set changing over time? So if you think about, this is your objective function. So you're going to optimize, so you iterate. Each iteration, you're going to compute the gradient, and then update the parameters. So the gradient, computing the gradient involves sampling a response and then updating. Okay, so now your parameters are different. So the next time you sample response, it's going to be, might be different now because it's coming from the new model. And if you sample multiple responses, those responses, that's going to be a different data set from a different distribution than where you started. So your data set, hopefully, is going to get better over time. So intuitively, even if you have this sparse reward, as long as you can get some of the easy questions correct, and you can get some reward, you can update your model, and you hope that the model can generalize beyond those examples so that next iteration, when you're sampling and solving a slightly more difficult questions, you're going to get a bunch of responses that happen to get the right answer, and now your data set will have higher and higher reward, over time. Okay, so this is in contrast to reinforcement learning with human feedback, where you use pairwise preferences, you estimate a reward model, and the reward model is generally a bit more continuous. It's going to assign essentially a numerical value to every response, how good it is. This is quite different than the sort of verifiable reward setting where it's sort of like correct or incorrect. And notice that, I'm sort of emphasizing this point that it's all reinforcement learning. It's all even kind of within the scope of language models. Sometimes you even use the same algorithms like PPO, but the intuitions for and for maybe how you set the hyperparameters and how you tune the model will be kind of different. Yeah?
So I noticed that the rewards are sparse, right? So you don't update the parameters if the reward is 0, is that correct? Then should we just set it to -1 so it goes the other direction? So we can use those rewards?
Yeah, so the question is, well, in this case, if the reward is 0, then you don't update the parameters. Why not make the reward -1? So at least you're kind of pushing the model away from those incorrect responses. This is something that will happen automatically when we look at baselines, because this is just a simple naive policy gradient where you're updating against the rewards. We're going to show that there's much better things than just using the reward. Yeah. Question? I think, yeah, question, and then I think there was a question over there.
Yeah, we know the reward only when we what's the whole response, the last word of the response.
So the reward is a function of the prompt and the response, the whole response.
Yeah, and we know the response is correct or not only when we generated it completely. So we have an idea only on the last token. Or...
So you're getting at sometimes you have reward before you even finish. And so the other type of reward is called process supervision or process rewards, which allow you to basically keep track of how well you're doing. There are things you can do there, and generally that's better if your process reward is good. For simplicity right now, I'm just assuming it's an outcome reward. But absolutely, if you have reward earlier, you should always evaluate the reward as early as you can if you trust it. The problem with process reward and language model is that you just don't, it's really hard to get a good process reward because unless you're completely going off the rails, it's hard to tell how well you're doing. Is there another question?
Kind of same question, what's the reward model here that we are working with? So How are we getting 0 and 1?
So the question is, what is a reward model? I'll show you some examples of this. Yeah, but you can think about the reward model as, which I think for your assignment you're implementing, basically the language model generates some stuff, and then you parse the answer out, and you check the answer against your answer key, and you return 1 if it matches and 0 otherwise. Okay, so maximize expected reward. Policy gradient sort of does the obvious thing. Naive policy gradient, does the obvious thing. But you have this high noise and variance problem. So a key idea in policy gradient methods is using what is called a baseline. And so recall that this is the expected reward. If you could actually compute this expected reward, you'd be pretty good, because then you could just compute that. But you can't, so you instead use unbiased estimate, which usually means ripping off the expectation, sampling a S and an A and ripping off the expectation. This is an unbiased estimate, but its variance can be pretty high. Okay, so just to give a toy example to appreciate what I mean by kind of high variance. So suppose you have just 2 states, so 2 prompts if you want, S1 and S2. And from S1, you have 2 possible actions. A1 gives you reward 11, A2 gives you reward 9. And from state S2, A1 gives you reward 0, and A2 gives you reward 2. Okay? So S1 fundamentally gives you higher reward, and S2 just gives you lower reward. And of course, the best policy would be in S1, you want to choose A1, and S2, you want to choose A2, right? So you don't want S1 and going to A2, but you notice that this 9 is actually larger than this 2. So you can end up in situations where each state, think about this as like a really, S1 as being a really easy question, and S2 is maybe a harder question. So you, just because something gets high reward doesn't mean you absolutely should be, updating aggressively against it. So if 9 is greater than 2, so if you're doing naive gradient updates, you might pick S1 going to A2, and you're just like, wow, this is great. I'm going to get 9 times the gradient. And then I look at S2, A2, and I say, well, that's only reward 2, so I'm pushing up that less. When in fact, if you look at the whole picture, it's clear that that's maybe just locally doesn't really make sense. I mean, I would stress that in expectation, if you look at overall states and actions, it all works out. The math all works out, but you have to look at kind of everything to get that. Okay, does this example make sense? Yeah.
Why would we choose A2 with the first screen, because A1 already has 11?
So the question is, why do you choose A2? So you're going to choose whatever your policy decides, right? So in a policy, when you're starting out, you don't know which is higher reward, so you're just going to maybe choose something random, right? So if you happen to choose A2, then you might upweight that and get reward 9. I mean, it's actually worse because you say, wow, reward 9, this is great. And the more you choose it, the more you're updating against it, and then you sort of get stuck in this local optimum where you can't even choose, there's no probability of mass left on A1 because you've updated against A2 so much. Okay, so here's the key idea behind baselines, is that you're just going to maximize the baseline reward. Instead of expected reward, we're just going to subtract off some B of S, okay, called the baseline function. So this is just the expected reward shifted down by a constant expectation of B of S. And the beauty of this is that this quantity doesn't depend on the policy pi. So even if you expand it out, you'll have a integral over P of S times pi A given S, but integral over A given S is just 1. So this is just, it doesn't depend on the policy at all. right? And so, of course, optimizing expectation R is identical to optimizing expectation of R minus this because it's just a constant. Okay, so that's the whole idea of baselining. It preserves the sort of optimization problem. And now if you do sort of naive policy gradient on this new objective, then basically you sample a S, you sample a A, and then you're just looking at this difference. Okay? So notice that this is true. This works for any BFS. As long as BFS doesn't depend on A, which it's not in the argument, so it can't depend on A, then this is valid. So now the question is, well, over all possible functions BFS, which one should we use? And let's just revisit this two-state example just to provide some intuition. I'm going to make some kind of assumptions. You assume your initial policy is a uniform distribution over all S and A, and your gradient of your policy initially is 1, just to kind of ignore that for now. So if you look at the variance over your gradients, you'll see that some of the time you get 11, sometimes you get 9, and sometimes you get 0, and sometimes you get 2, and the variance is 5.3. Okay? So if you define a baseline, which is 10 for S1 and 1 for S2, then let's see what happens. So you subtract off the baseline from these reward values. So for S1, you subtract 10. For S2, you subtract 1. So now the baseline variance is a lot less. It's only 1.1. So we reduce the variance from 5 to 1, which is pretty good, by just subtracting a baseline, which again doesn't affect your end results in expectation. Yeah.
So I think there's the assumption that this expectation of BFS doesn't depend on the policy pi. So I was wondering if it is okay still for us to initialize B as, let's say, the very original frozen policy.
Yeah. So good question. So BFS is not supposed to depend on policy, but your question is, can I just take an initial policy and set BFS to that? So absolutely. So it's one of these things with reinforcement learning you have to be a bit careful of is what's constant and what's not. So you can always take a frozen model and say that's a constant. And as long as your expression doesn't depend on that, that's actually treated as a constant, like you're not differentiating through it, then it's all fine. Which means also that if you are sampling and you're performing the update, that you have to kind of keep an old copy of that policy. Because if that thing is changing, now you can get into these weird settings where it's not actually a constant anymore.
And then a follow-up would be what if we initialize pi as sort of the policy from the last gradient?
Yeah.
Instead of the very, very original.
Yeah, so you can do this. So typically what you do is you essentially have a policy. It's kind of an old policy or a anchor for a while. Or if you're doing PPO, you have a value function. And then you kind of hold it for a while, and then you do some updates, and then you kind of update it on. So, in practice is what you do. Part of this, it can't depend on A is really for the theory kind of to work out. But in practice, there's all sorts of things that people do. Okay, so what we showed is that, at least for this example, anecdotally, you can define some baseline that reduces the variance. So this is kind of giving you hopefully a concrete sense of the power of a baseline. In the lower variance you have, the faster the convergence. Okay, so you might wonder, what is the optimal baseline to use? And if you do some math, you realize there's actually a very kind of nice closed form solution for this. This is written for one parameter models. If it's multi-dimensional, I think you have some covariances. And this is just expectation of this derivative squared times r divided normalized by the same expression without the r. Okay? So this is, in general, kind of annoying to compute, especially if you have high dimensions. And because this thing is going to be some sort of like, covariance. So typically what people do is you just ignore this stuff and you say, well, I'm just going to try to, I'm going to set baseline equals expected reward divided given S. Okay, so this is not optimal, but it's kind of like a good heuristic. And even this is, you can't compute this, right? Because anything with expectation, you can't compute, you can only estimate. But this is now, I think, a good guiding principle for what you want your baseline to be. It's the expected reward given your state. Okay? So just to recap, we said we have the naive policy gradient. We can introduce this baseline as valid for any B of S, and now we've come to a conclusion that maybe this is like a good choice if we can try to get a handle on expected reward given S. Okay, so this particular choice has connections to advantage functions. So in reinforcement learning, you typically have a value function, which is the expected reward given a state. And then you have a Q function, which is expected reward given a state, and I've taken a particular action. And note here that Q and R are the same because we assume outcome rewards and A has all the actions. In general, R is going to be like the returns from that state rather than just a single reward. Those two are same for now. And the advantage function is just defined as the difference between the reward I would get if I took action A and sort of if I average over possible actions A. Okay, in particular, it's measuring how much better is action A than the expected value that I get from S. What is the advantage of taking A as opposed to just going along with a baseline? Baseline is ambiguous. We're going with a policy. Okay, so then if you look at B equals this sort of heuristic form that we talked about earlier, then the baseline reward, where you just subtract off B of S, is identical to the advantage. So you can interpret the baselining if you have the advantage, if you have this sort of, this choice of baseline is identical to optimizing the advantage. All right, so that's just to give you some intuition behind what this baseline is doing. In general, we are probably going to deviate from that because we can't estimate we can't compute these expectations exactly, so we're going to do something else. So in particular, I'm just going to let delta denote whatever thing we put in to the estimate. So all of the methods are going to basically take the gradient of the log policy and times something that's going to be based on the reward. Okay, so all the algorithms you see, PPO, GRPO, have this sort of form where you rolled out and got an action, and now the question is, how much do you want to move towards that action? And it's going to depend on the reward. Okay, so you can put the reward here, then that's naive policy gradient. You can do reward minus some estimate of the expectation, and you can also divide by the standard deviation, which is what GRPO does, which we'll see later. Okay, but this is sort of the general form. And so the exact form of GRPO isn't that important because next year there's going to be GRPO2 or whatever. But all of this like policy gradient stuff is, I'll be giving the same lecture next year. Okay. All right. Speaking of lecture, you can check out Chelsea's deep RL class for a few more derivations and intuitions about RL in general. Okay, so any questions about policy gradient and baselines and advantages? Yeah.
Just for the Tatsunori, the baseline is like a baseline reward. That's what baseline represents.
So what's the definition of a base? The baseline is any function that B of S, which only depends on S and not A, that you're essentially sticking into a policy gradient algorithm. You can think about it that way. So basically, you update, policy gradient will update based on this, and baseline is whatever function you choose there. So those of you who have seen kind of control variates, this is basically the same idea from statistics. Okay, so now let's try to dig a little bit deeper. We're going to actually define a simple model, a simple task, and actually walk through some code that may or may not look like assignment 5, and we'll try to hopefully do some runs. Okay, so a lot of this exposition is based on the GRPO algorithm. So this slide I might have to update next year, but it's sort of trying to generalize it beyond the particular choices here. So GRPO, remember what Tatsu said last time, it's sort of kind of interesting lineage where you had PPO and then people did DPO, and GRPO is a kind of a simplification of PPO. As opposed to kind of algorithms, you start simple and then kind of grow in complexity. But really, I think GRPO exists in 2024 as opposed to, in 2000, I think it was 17 or something when PPO was introduced, is because the language model setting provides some kind of natural structure that motivates GRPO. You can't really do GRPO naturally, I think, in classical RL settings with like the robot trying to walk. And the particular thing is that in the language modeling setting, you have a prompt. You can generate a bunch of responses from that prompt. And this gives you a natural group structure to compute essentially the baseline, which turns out to be the average over the rewards, right? The whole point is that you're trying to kind of minimize the variance. And the group is a kind of a natural comparison set. That's why this is kind of relative. It's relative to the group. Whereas if every rollout looks different, there's no natural group structure, then GRPO doesn't really make sense. And you have to find something else, and that something else generally tends to be a value function, which aggregates over all the possible states and actions. In here, this case, you kind of have an empirical estimate over all the possible responses without considering everything because of the LM setting. Okay, so here's the pseudocode. We're going to look over it in actual Python in just a second, but I'll just flash it up here. Okay, so let's define a simple task. I wanted something simple enough where I can actually train a very simple model on my laptop without, and running a language model transformer wasn't gonna, I don't have a fancy laptop, so that wasn't gonna happen. So here's a simple task, sorting n numbers. So the prompt is n numbers, and the response is n numbers that are hopefully sorted. So now you have to define a reward to complete the definition of the environment. And the reward should capture how close to the sorted ground truth the response is. Okay? So immediately you actually see one of the interesting things in reinforcement learning is that you can define a reward in different ways. So for example, you can define a reward which is like 1 if it's sorted and 0 otherwise, which is presumably what you care about, but you're going to remember the sparse reward problem. If you start out with a policy that doesn't do anything, you're mostly going to get 0 reward, and you're not going to really make much progress. So let's define a reward that gives partial credit. So we're going to define a reward that returns the number of positions where the response matches the ground truth. Okay, so you basically the code looks like this. You look at the ground truth, which is the sorted of the prompt, and you just count the number of positions where the response matches the ground truth. Okay, so the reward for the correct answer is 4 because 4 positions match. If you have this thing that doesn't really solve the task, then reward is 1 because I think you got lucky and you put a 2 in the second position. And you have this thing which also is not solving the problem, but you kind of look at this and say, well, it's really trying. And again, you get a 1 because the 0 is in the right position. Okay, so that's one reward you could use. Maybe you're kind of unhappy with this because this is pretty far off, and this is closer, but yet they're all getting reward 1. So let's define an alternative reward that gives more partial credit. So what I'm going to do here is I'm going to give 1 point for each token in the prompt that shows up in the response. Okay, so at least output the tokens that are in the input. Not too much to ask, right? So for this particular example, I get an inclusion reward of 4, and then I'm going to give 1 point for each adjacent pair in the response that's sorted. So that's a 3 because there's 3 pairs, adjacent pairs, and the reward is the sum, so that's 7. So if you're kind of paying attention, you realize that this reward is actually has a loophole in it, but I'll let you figure that one out. Okay, so now this particular very wrong answer gets a reward of 3, and this one gets a reward of 6 because it's really trying its best, and we give a lot of partial credit for RL algorithms. Okay, so that's the task, and in general we're going to go with the second reward function. Okay, so the task is clear. That's an environment. So now let's define a model to solve this task. And so we're going to define a really simple model. We're going to assume the prompt and the response length are fixed and of the same length. When I was trying to iterate on examples, there was one I was doing some sort of dynamic thing, and it was just like annoying to do. So I simplified it. I'm going to try to capture positional information with separate per position parameters because obviously position is the kind of the name of the game here. Or position matters for sorting, obviously. And one thing I'm going to do is decode each position in the response independently. So this is not our regressive model. I'm just going to encode the sequence, and I'm just going to output all the tokens separately. Not what you want to do generally in real life, except for, I guess, in some speculative decoding, it can be helpful to do this in limited doses. But it makes the code a lot cleaner because this auto-regressive generation, that's a part which was getting really hairy. So just try to simplify it. Okay, so here's the model. So I have the embedding matrix. I have, for each position, I have a matrix for basically transforming for decoding and a matrix for, encoding and then decoding. Okay, so that'll be easier to explain as I look at the forward pass. Okay, so I start with a prompt. I'm going to use this notation in general to denote the dimensions of the tensor here. So there's a batch dimension, which is the number of examples, and number of prompts, and then a position dimension, which is obviously the position I'm in. So I'm going to generate responses. So this is inference. So let's walk through this. So just some terminology. So I have a batch size, which is the number of prompts here. Each prompt has a particular length, 3. Number of responses per prompt, I'm going to generate, in this case, 2. And the response length is 4. In the sorting task, this response length is going to be identical to the prompt length. Okay, so first I'm going to pass the prompts through the model to get logits, which is going to give me for each prompt and each position a distribution over tokens. So what this looks like is I'm going to embed the prompts into this dimensionality. Now I'm going to transform using the per prompt position matrix, and I'm going to collapse it. So using, einsum, I have batch position dimension 1, and then this weight is per every position. I have this dim1 to dim2 transformation, and I'm going to end up with batch dim2. Okay, so I've kind of summed out the position and dim1. And then given that vector for each prompt, I'm going to, for each position, apply this matrix and get back a vector. And then finally, given a vector for each position and prompt, I'm going to convert that into a logits over my vocabulary. Okay, so it's kind of a simple model I made up. I don't know if it is actually anything useful, but it fit this, sort of did this toy example. Okay, so now I have logits, and this is just kind of shenanigans to deal with the fact that torch multinomial needs something flattened. So I'm going to essentially basically flatten this into a batch times position by vocab. I'm going to sample num responses, and that's going to give me batch position number of responses, which I'm going to call trial is that dimension. And I'm going to basically rearrange things to make it so that it's for every prompt, for every trial, I'm going to get a sequence of examples. Okay, so maybe I'll pause just to check that everyone's with me. So this is nice. This is usually where you would call out to a VLM, right, and do the inference. I'm just doing this here because it's like a very simple model, and I can everything's just like matrix operations. Yeah.
The responses are going to be very close by, right? We are kind of sampling from the same logits. The responses are going to be close by.
The responses are going to be close by, so we're sampling num responses independently from that distribution. So they're definitely going to be similar. But that would be the same as if you sample from a language model as well. The only difference between a language model is this are regressive and this is independent.
Basically, the point was, shall we change the temperature? Basically.
Yeah, so you could change the temperature. You can do various things. I'm trying to be kind of faithful to the algorithm. Okay, so I get my responses. I can compute a reward over all these responses. And this basically goes through, and for every prompt and every response, I just call this reward function, which we looked at earlier. Nothing too interesting there. Sorry, this is a little bit long. Oh no, okay. Well, this part is going to be far less interesting because I thought I fixed the random seed. Just generally, you wanted a little bit more variance in the rewards. Anyway, so the rewards all happen to be 3. So this is going to make some of this other stuff kind of less interesting. But nonetheless, I'll go through the computation here. There's this function called compute deltas, which takes the rewards and converts them into the delta that I'm going to use for my updates. And the framework is, there's many ways, many choices here, which some of which you'll explore in your assignment. So for example, if you can just return delta equals the rewards, you can center the rewards. So you can compute the mean over all of the responses for each prompt. So this is what this is doing. And then you can just subtract off the mean. That gives you center rewards. And to answer a question from earlier, this is where if your rewards look like 1 and a bunch of zeros, your average is going to be like let's say 0.1, which means that if you subtract that, now you're going to end up with a bunch of minus ones and something that's slightly below 1. And therefore, you're going to perform updates on all those negative examples as well. Okay, so that's centered rewards. And then you can do this thing in GRPO where you normalize. So you center the rewards, and then you divide by the standard deviation and add something small so you don't divide by 0, just in case. And you return that. Okay? So one thing to notice is that what happens if all your rewards are 5, for example? So rewards is just going to be 5, so you're going to make a bunch of updates. Centered rewards is going to be all 0, right? So that means you're not going to make any updates. So this is kind of interesting to think about. If you have an example where your policy is generating everything is the same reward, then you're actually not going to make any updates on that example. And the intuition, it might or may not make sense depending on what you're trying to do, but the intuition is that there's no gradient. In terms of relative comparison between that group, there's no reason to favor any particular example more than another one. So you're just going to abstain and hope that some other examples give you some signal. And the normalization means that if all your rewards are, let's say, 10 versus all the rewards are, if you multiply all rewards by 100, then the normalized rewards is kind of invariant to the scale of the reward. So I think that's the good thing about that. Just for fun, there's another thing which the GRPO paper didn't do, but you might think is kind of a cool thing to do. So you can zero out any reward that isn't the maximum for each batch as well. So the idea here is that often in reinforcement learning, sometimes you really get into these local optimum where if you assign too much partial credit, then the policy is going to sort of latch onto that and go after the low-hanging fruit instead of the kind of the thing that would give you more reward. So you could try to kind of just say, well, if it's not getting the maximum reward, then I just don't want that. It's kind of an all or nothing thing. Okay, so far what we've done, we generate a bunch of responses, we compute rewards and these deltas, which allow me to provide the update. Now I need to look at the other piece, which is the log probabilities of the responses. Because remember in the gradient, policy gradient, I have delta times the gradient of the log policy. So this part is also fairly straightforward. I pass this through the model, convert the logits into log probs, and then there's some shenanigans to because the prompt is only batch pause and responses has an extra dimension in there. So I'm just going to kind of upcast these log probs to that higher dimensional tensor, and then I'm going to index log probs using the responses. So the responses basically for every batch trial position specifies the index into log probs that I need to get. So this is batch trial pause vocab, and this is batch trial pause with an index, and that will give me batch trial pause. Okay, so this gives me, logits that are returned by the model give me a distribution over all the vocabs for every position and prompt. And now I have log probs for the particular responses. So these are log probs for these particular responses I got. Okay, so now we want to finally compute the loss. And the loss is just going to be, and here there's another set of choices here. So I'm trying to present this as a kind of a menu of sorts. So the most naive thing is, this is naive policy gradient. You just take the deltas and the log probs, and you just multiply them together and average. Okay? So this is log probs. Remember, batch, trial, pause, and deltas is batch, trial. And this is because it's outcome reward. You only get, there's no position dependence on the deltas. So basically every position gets, the deltas get broadcasted to every position. If you had process reward, then this deltas would be kind of per position as well. Okay, so that's the naive thing. Just as kind of an interlude to make sure that we kind of into this idea of freezing parameters. So later we'll see in GRPO, you see these kind of ratios, right? This kind of relates to this idea that you have a probability of action given S, and you're dividing by some kind of other model. And it's really important that you can remember to freeze and not differentiate through P old. So just give you a kind of toy example. Suppose I have a single parameter W, and that drives both the probability, think about this as a policy, and also there's like an old value, which in this particular iteration is just the same thing. And now what happens if I compute the ratio and do a backward pass? What would the gradient be? So I'm dividing P by P old. So the ratio is going to be 1. And the gradient of 1 is 0. So what are the... Okay, so it's 0, which is obviously not very helpful. So the way you do this properly is that you have your P as usual, and then anything you want to kind of treat as a constant, you wrap in this no grad, and then this allows you to get the value of, but not the whole computation graph, and you just divide by that, and now the gradient is not 0. Okay? So just like a kind of be careful when you're, because in RL as opposed to when you're doing pre-training, there's many different values that all depend on different either old or not old parameters. Yeah?
Don't discount like an outcome in one sort of when we go backwards through the sequence. Like, I guess when you always have a hypothesis that like the last 100 tokens matter more than the first 100.
So the question is, why don't you do some sort of discounting when you have outcome rewards? So maybe the last 100 tokens matter more than the first 100 tokens. I think that is not so clear. I mean, certainly like the last tokens where you're literally generating the answer is important. But I think the problem is that in reinforcement in general, you have to do credit assignment, right? There's certainly decisions early on that matter. In fact, they might even matter more than what you get. Because if you basically have the right strategy, then the stuff that happens at the end maybe just follows out. And the hard part in reinforcement learning is that you don't know where to do the credit assignment, especially when you have a sparse reward. So I think in this setting, we're just going to smear the credit all over, or the blame all over the place. Okay, so with that kind of interlude, so this is important for computing the GRPO loss. So imagine we have an old model, okay, with so this is an old checkpoint. And using this old model, we're going to compute the log probabilities of the responses. So that gives us the old log probabilities. And now, let me just skip the unclipped version. So this is the GRPO loss. Okay, so let's step through it. So it's the clip version. So you look at the log probs and you divide by the old log probs, which remember should be a constant. Actually, I sort of didn't follow my own advice. I don't think I wrapped the old log probs in with no grad, but anyway, you know how to do that. So you look at this ratio, and then that ratio gets multiplied by delta. Okay? And so if you contrast with the naive thing, you're just multiplying log probs times delta. So this is basically the same thing, except for I've divided by all log probs, which is constant. So I'm just scaling the gradient. But now there's the other part, which is I'm clipping. And the reason I compute these ratios in the first place is that I'm going to clip the gradients between 1 minus epsilon and 1 plus epsilon. So this is to make sure that the ratios don't go too out of whack. And I'm going to also multiply these clip ratios by delta. And I'm going to take the minimum and return it. And there's a negative sign because I'm talking about rewards and convert that into a loss. Okay? So this is just following the kind of the math in the GRPO paper. And in the assignment, you'll see this kind of explanation of why this makes sense. So if your updates are within the clipping range, then you just get the kind of the standard update. But if your ratio is outside, then the magnitude of your updates are going to be bounded by 1 minus epsilon and 1 plus epsilon. Okay. So there's also this KL penalty, which provides additional regularization. Just a kind of a quick little math exercise here. So remember the definition of KL between two distributions. It's your sample from the first left distribution, and it's log over the left over the right. Rewrite that as Q over P with a negative sign. And then, so if you're doing KL penalty, you could just use this directly, right? But there's this, and if you want to estimate the KL, you can just take strip out the expectation and you get an unbiased estimate. It turns out that this particular estimate can have lower variance, where you just do Q over P minus the log minus 1. So it looks a little bit weird, but you can sort of check that this is identical. Everything's equal because expectation Q over P is just 1. So this part is just 1, and you subtract 1, which is 0. So you're just left with this original term. So the math works out, and the inside just gives you a better estimate of the KL than doing this kind of naive thing. So in a lot of cases, when you're trying to find these estimates of the expectation, you're just trying to find an unbiased or sometimes even biased estimate that has lower variance than just doing the naive thing. So you kind of try to rewrite the inside to so that it reduces the variance. Okay. So just a quick implementation of the KL penalty. This is pretty straightforward. The only thing you have to pay attention to is you're summing over the last dimension, but taking a mean. So you're summing over the vocab, but you're taking a mean over batch trial and position. Okay, so just to kind of summarize so far the components that are needed to introduce the actual algorithm. You generate the responses given a particular fixed model. From the responses, you compute the rewards and the deltas. And in the case of GRPO and friends, these don't depend on the model. It's just like a function of the responses. And if you think about kind of architecting this system, sometimes the reward is very simple. It's just like a one-liner exact match. Sometimes the reward will involve like an agent like executing an environment and doing all sorts of crazy things. So this could be, expensive or cheap operation, but it's independent of the actual model unless you have like LM as a judge, which case that's another model. Simultaneously, you can compute the log probs of the responses, and then you compute the loss from the log probs and the deltas that you got here, and you combine them, either clip or not clip, or you normalize, or you sorry, that's up here. So you either clip or don't clip. And then you take a gradient, step. Okay, so let's try to put this all together. So this is the full algorithm, which is essentially a implementation of what's in here in code. So there's some boilerplate I'll just skip over. So I'm going to define, some trivial data set here, 3 prompts of length 3 each, and then define the model, optimizer, and then I have there's multiple loops here, and GRPO. So there's an outer epoch loop, and here, if I'm doing sometimes if I'm doing a KL penalty, then I'm going to kind of freeze the model and have that as a reference so I can regularize towards that. And then otherwise I sample the responses. So we talked about this. We compute the rewards. We compute the deltas depending on what variant flavor you like. And if you're doing the KL penalty, then you also need to compute the log probs under the reference model. If you're doing if you're doing some sort of clipping, then you need to compute also the log probs under the old the current model. And then you take a number of steps given the responses. So the idea here is that often remember inference is expensive, you generate and you want to do a bunch of gradient steps with respect to the responses. Okay, so this inner loop is basically taking a bunch of steps with respect to the same set of responses. And to do that, you compute the log probs, you compute the loss. If you want, you can add a KL penalty, which sometimes helps, sometimes doesn't really make a difference. And then you just optimize. Okay. So that is, maybe I'll stop and answer any questions people have about the setup here. So the big picture is that you have the outer iteration, which you ignoring the KL penalty because there's another wrinkle I'll mention later. So you generate a bunch of responses, and then you quickly do a bunch of iterations on them. And you generate a bunch of responses and do some iterations. That's kind of the basic idea. Now, there's an additional thing which, if you have the KL penalty, then you actually regularize towards a reference model, which is changing even slower than this outside model. So the way this is written is actually slightly different than the GRPO code. In the code, you actually have 3 loops. I only have 2 because I'm sort of just updating the reference model, it's a little bit kind of infrequently. And I'm also not doing, this part. Okay, so there's a few implementation details, but hopefully you could kind of get the rough shape of what this looks like. So you actually have kind of 3 models. You have the reference model that you're doing KL regularization against, and then you have the old model, which you're using to compute these kind of importance ratios between the current model and the old model, which you're also freezing, and then you're kind of updating the current model online. So one kind of annoying thing about the reference model is that you actually have to store a whole copy of the model, which is can be just doubles your memory. The old model is actually a little bit better because you just remember if in the code you actually don't have to copy the old model. You can just generate a bunch of responses and compute the log probs on those responses and just store the log probabilities, because those are going to be, you're dealing with the same responses in the inner loop. So you don't have to store a whole copy of the model. You just have to store the log props. Okay, question?
Why don't we do KL divergence between old policy and the latest policy instead of doing it at these
So the question is, why don't you do the KL penalty against the old instead of the reference? The way to think about this is that let's see. So remember how we said we define an objective function in reinforcement learning and we optimize it. It's sort of a little bit of a lie because really you just define this objective function so you can compute a gradient. And the gradient you compute and you update for a while, but then your kind of objective function changes, right? So, so really you can think about, let's say, so this point, you fix a reference model, and then you write down this nice objective function, which is, let's see if I don't have the full expression here, but the expected reward with all the, expected reward, and then the KL penalty. So if you change that too quickly, then it's, I guess the more you change that, then the less you're actually like optimizing that objective function. So that's, I guess, maybe one kind of reason. I mean, honestly, I think, empirically, it's sort of a gradient because depending on how many steps you take here and how often, you can make it either more like pi old or less like pi old. I mean, you sort of have two kind of mechanisms for regularization. One is the clipping thing, which is applied to pi old, and then the KL, which is applied to pi ref. Okay. Yeah, question?
For the first iteration of GRPO, for the most inner loop, isn't pi theta old equal to pi theta? Is it like way small to do that?
So the first iteration pi old is equal to pi theta.
Yeah.
So you're essentially going to, well, you're still performing an update. You're just scaling by some, remember pi old is, from the point of view of the update, is just a constant. And I guess the only thing that matters is that you're not going to get clipped because the ratio is 1, so you're just going to guarantee to make an update. So yeah, it's fine. Okay, so maybe just to kind of round this out a bit. So run some experiments. So you run the same piece of code that I presented. I'm going to do 100 epochs. Number of steps for epoch is 10. And we see this kind of learning curve. So just to maybe walk through what this is doing. So on epoch 0, step 0, we have this prompt. The responses, it generates a bunch of stuff. You score them, you compute the reward, and then you compute the delta. In this case, it's identical to the reward. So I'm going to update towards the 3s a little bit more than the 2s. And then you see this prompt, kind of the same thing. This one, I'm still going to update against all these, towards these responses, even though they all have reward 3. And then let me scroll down and see what happens. Eventually, you see that I'm getting reward 3, but this is not, looking. I mean, it's not really sorting. Is a short answer. It's producing numbers which are sort of more or less in the prompt, but not really sorting. Let's see how it does at the end. So it's not terribly great. I actually haven't looked at the other examples, so it'll be exciting to see what happens here. So here we're using the centered rewards. And see the mean reward is getting higher, so it's like past 3 instead of 2, which is promising. So let's look at this run. So notice here that I generate some examples. Reward is 2 and 3, but because I'm centering, I'm sort of pushing the model towards the ones with reward 3 and away from the ones that have reward 2. So this is what centering is doing. And if they're all the same, then centering doesn't really is actually going to be a no-op, whereas before I was performing updates, which is kind of silly, I think, because if you think about it, I'm sorting 1, 2, 3, and here all the responses are equally bad. So updating towards these don't really maybe make as much sense. Let's see towards the end how this does. So still not, I guess it's not great, but it's got a little bit higher reward. I probably need to tune this a little bit more. But at least it's getting reward 4 here for getting the right numbers, and 0, 1 is, it's not the most unsorted. Here I think it's sort of getting the permutation right, and here I think it just gets stuck. And at this point, you see all the deltas are 0, so like more training isn't really going to help on this batch. But if you regenerate, maybe you'll get some fresh samples and be able to update. So you can see that's kind of like the partial reward is sort of a double-edged sword, right? Because I'm giving you 4 points. So it's like it's good reward, but I still didn't solve the problem completely. So I think you have to be careful with reward, dishing out reward. And then finally, the standardized. I think the normalization here didn't really do all that much, so I'm going to skip it. One thing to I think note is that if you look at these loss curves, you think, well, this looks kind of good, but why is this looks pretty bad, even though the reward is going up? And this goes back to kind of my statement that minimizing the loss is a little bit of a lie here. It's not like we were minimizing one loss function that you can measure over time. Because the set of responses is changing over time, you don't have really kind of a reference point for the same loss. I mean, you can measure loss on maybe some validation set, but if you only have rewards, then you're sort of back to only being able to rely on reward. Because even think about it, even if you have a bunch of examples where the model is just happy generating them, it's sort of like the loss is only respect to what the model is generating. So it's a kind of a self-circular thing. So monitoring the loss is not really kind of such a meaningful thing to do. Okay, so maybe just to wrap up here. So reinforcement learning, just popping back up, I think it's really exciting because it's really, I think, the key to making models that actually surpass human abilities in some sense, because label data is only going to get you as far as mimicking the behavior that's presented in the label data. I think the model is, if you can measure it, you can optimize it. If you have a reward, I think there's optimization, as we've seen even with the sorting examples. I mean, can be challenging in itself, but there's also perhaps a bigger problem is, how do you design rewards that are not hackable in environments that are, generalizable? I think that's a pretty active area investigation. For the optimization part, I mean, the sorting isn't that hard. I think I just ran it for like 20 seconds on my laptop, so you shouldn't expect greatness. I think, just to review the policy gradient framework, I think is conceptually clear. You write down the expected reward, you subtract the baseline, it's the same thing. And then you just, you try to find a, estimate of that reward or advantage. And that's one thing that we didn't talk about, which I think is actually important, and maybe next year I should try to do a bit more of this, is that building RL systems and scaling is actually much more complicated than pre-training. And the reason is that you have to do inference. And inference is its own can of worms. You also have to manage multiple models. So you have the policy you're training, you have, if you have PPO, then you have the critic. If you have the inference and you have maybe an inference worker, then you need to ship the model over there to run the inference. If you have like an agent environment, you have like the environment which requires spinning up. And then on top of that, you also have like the PyOld and PyRef. So you have multiple models that you need to keep around. And on top of that, you have to do everything kind of in parallel and distributed and make it all sing and dance. So there's a lot to be done there, which we're not really going to have time to talk about in this class. But if you're interested, there's definitely pointers I can send you to. All right, so that's it, and see you next time.